Let's do load calculations of a single family dwelling. We're going to be using the standard method in this example. And we're going to be using this worksheet, which is going to make this a lot more understandable. You're going to be able to visualize it better, and it'll help us out. Okay. So the question wants to know what the minimum overcurrent protection device for a dwelling unit is. An overcurrent protection device is your breaker. So when it's talking about this unit, it's talking about that main breaker that's going to shut off all the power. I'm going to start off by filling in what is known as my general lighting load. And for this, I'm going to basically show you how I do it with some explaining. And then at the end of the video, I'm really going to actually go into the code book, show you what's going on, and so you can see the tables and the articles that'll explain to you the code. So you maybe can read it and get this in your noggin a little bit more. But for now, I'm just going to show you how I do it. So we have square footage of the dwelling, which we saw was 1,200 square feet. Okay, so what we do is we get our 1,200 square feet is quantity right there. Then we take our square footage of our dwelling and we multiply it by 3 volt amps. So 3,600, 3,600, just timesing by 3. And then, well, it doesn't mention anything about a small appliance branch circuit. It messed me up because I'm used to calling it a small appliance branch circuit. They call it small appliance circuit. And then our laundry circuit. And if you read this over, there's nothing about a small appliance circuit. There's nothing about laundry. Okay? So what we're going to know is that you usually have at least one laundry in a building. So we're going to just call it one. And you usually have 2 small appliance branch circuits, and you, to code, have to have at least 2 small appliance branch circuits. So you times both of those by 1,500. So the first one is 3,000. The second one is 1,500. And since this is something you commonly see, I would just remember the number 4,500. So all you got to remember is your square foot times 3 plus 4,500. That'll give you the answer. Okay, so let's do that. Yeah, it might be easy to do this in your head, but I highly recommend doing it on a calculator. No mistakes. So we're going to punch in those numbers. 3,600 plus 3,000 plus 1,500. Okay? We got 8,100. So 8,100 is the total volt amps of all that added together. Okay? That is your general lighting load. That number. Okay? But now, in the code book, which I'm going to explain all later, so we take our total amount, general lighting load, we're going to subtract 3,000 from that. Okay? So now we have 5,100, or 5,100. Okay? So now we got our 5,100, and we multiply it by 35%, which is 0.35. So 5,100 times 0.35, we get 1,785. And now that 3,000 that we took away, now we add it back to this number after we do this 35%. So let's review that one more time. We get our general lighting load, which is just our square footage times 3, plus 2 small appliance branch circuits always, and 1 laundry circuit always, so 4,500. So 3,600 plus 4,500, 8,100, minus our codebook tells us 3,000. We get that answer. We multiply that by 35%. We get this answer. And then that amount that we took away, we just add it back. So now we're looking at 4,785. Okay, so that is our total demand load for lighting. And as you can see, That's basically half of the original general lighting load, 8100. Now we have 4785. So we cut that down quite a lot. Okay, let's move on. Okay, now we have this section, which are fixed appliances. Your fixed appliances are electrical appliances that are installed, but they are fixed. They're not going to be moved around. So fixed appliance would be like a bathroom fan, a dishwasher, a disposal for your sink, a hot water tank in your garage heating up your water. You know, those sort of things, those are your fixed appliances because you're not just going to, at any given point, pick those up and move them. They are fixed. So let's go over this just for a sec, just so we kind of wrap our head around it. So our kitchen, which is known as our small appliance branch circuits, are basically things like your blender, your coffee maker, just little things like that that are going to actually be connected to your kitchen circuits. Okay. Okay, next we're going to identify anything that says 240 volt and 120 volt. I highlighted it just to make it quick and easy for your eyes. So right here we do have 240 volt, that is your AC unit, so that's not your fixed appliance. But we have a 120 volt quarter horsepower attic fan. So that is 120 volts. Pay attention to that. You're gonna need to pay attention to that. So what's good to know is that these other ones just say kilowatt and watt, stuff like that. So we already have it mathed out. But if they give us just our amps and our voltage, we're going to multiply amps times volts to get power. I hope you know what this means. P is watts, I is intensity of current, E is for electromotive force. So, other words, wattage, amps, and voltage. If you don't know this, you got to study this before you're here. You shouldn't be here if you don't know this. Okay, so now let's put that in our fixed appliance loads. Okay, so we have all this written down. Here's our watts. And then here's our volt amps, which are the same thing. So anything that had watts already on it, I just transferred it here. If I had a horsepower, I just wrote that here where it says watts. So then I know that I got to math that out. And I don't transfer that here yet because I don't have the answer. Then those are all my 120 volts. So you got to pay attention to it. If it does not mention it, it's 120 volt. And it will mention it if it's 240. So it did mention that this was 240 and that it was 4 kilowatts. So I transferred it over. I wrote kilowatt here and then I transferred the actual number here. So from 4 kilowatt, I did 4,000. I did that here as well. Okay, so let's math out. Well, first, let's talk about this. There's two missing from here. There's your bathroom fan and there's your grinder motor. There's a reason for this. Okay, so if we look at our grinder motor and if we look at our attic fan. Oh, not attic fan, bath fan. Okay. So there's two missing from here. Let me re-say that. There's your bath fan and your grinder motor. So if we go over here and we look at bath fan, we have a 450 watt bath fan. We have a 1/6 horsepower grinder motor. So the code tells us if there's anything under 500 watts or under a quarter horsepower, which both of these lie under that, we do not math out a 75% demand factor. Okay? So because of that, I drew these over here separately because they're not going to get a demand factor. You'll see in a second. So let's first get all of our answers. We still have our quarter horsepower attic fan. So what we need to do is we already have our volts, which is 120 volts. That's why we put it here. So to find watts, we're going to need to either find our resistance or our amps. And there's a way to find our amps. We're going to open up our code book to 430. Oh yeah, 430 part 14 motor full load current tables. So we're going to flip right to that. We do not use direct current motors. We're not dealing with direct current. It did not mention DC, so we're doing AC. Okay, so here we are. It did not mention three-phase. Okay, so we're doing single phase. And we're doing alternating current. We're doing AC single phase. It's full load current in amps. So this is the table that we use for this. Okay, so we have a quarter horsepower. A quarter horsepower is 5.8 under 115. So 115, that might leave you with the question, so do you multiply your amps times 115 to get your watts? No. If you see 115, if you see 230, do not take into consideration of your calculations. Your calculations will use 120 volts and will use 240 volts. That's all you need to know. So all we're going to do is we're going to get our 5.8 for a quarter horsepower, and we're just going to multiply that by 120, and we get 696. Okay, there we go. Now we have all of our watts for anything that is over 500 watts or our quarter horsepower or more. So that's all here. Now what we do is we're going to add all of these numbers together, and if there's 4 or more appliances, any of these, if there's 4 or more, we're going to multiply by 75%. Let's do it. I'm just doing it with you. So 1200 plus 800 plus 1000 plus 696 plus 4000. And while this is on my mind, I kind of want to mention this now. I've been studying this for some years, so if you don't get this right off the bat, don't you worry. I am years into this. I am just young. Okay, so let's add all these together. Boom. We got 7,696. So now we get that 7,696. We multiply it by our 75% demand factor. I'll explain demand factors a little more at the end of the video. So we get 5,772. Okay, now that's done. Now we can move on to this. So we're going to do the same thing for this, where we have a 6 horsepower grinder motor. So we're going to go here, which specifically is table 430.248, and it is on page 332 of the 2020 NEC book. Okay, so we have a 6 horsepower. So let's do that. It didn't mention 120 volts, 240 volts, or anything like that. So we're going to use 120 volts. We got 6 horsepower. We got 4.4 amps. So we're going to do that 4.4 amps, and we're going to times that 4.4 times 120. And we're going to get 528. Okay, so now that we already were given before our bathroom fan wattage on that paper, it literally just gave us the answer. So we had our 450 watts, since that was under the 500, it's here. And then, quarter or less, so that's why this is here too. We just did 528, so now we have both of our watts. Let's add them together, and this will be our answer for our not demand factor of anything. We're going to do this at 100%. There's no demand factor. We're not taking anything off. Okay, so for that one, we have 978 watts. So now we can move down. So here we have other loads, and we have heating/cooling. Other loads contain range and dryer. Heating/cooling contains heating and AC. I'm just going to do it in order. So I'm going to start off doing the range, and then after that, I'm going to go to the dryer. Make sure you pay attention to quantities of things. Are there 2 dryers, 3 dryers, 1 dryer? Okay, so here we're starting with range and then dryer. So we have our 8,000 watt range. Okay, so it already tells us the answer, right? No. For ranges, we got to go in the book. Remember, all this will be explained later on. So now we go to table 220.55, which is on page 78. So what we do here is you need to know a rule here, basically. It tells you, but I'm going to explain it. Less than 3.5 kilowatt rating. Less than. So if it's this or more, you don't choose this. Here's your rating. Okay, so what is this rating? This is just percentage on the yellow. So yellow is percentage. Remember that. I would highlight it the same way that I did. Okay, and then I highlighted here yellow demand factors, just so in your brain it's real simple. Okay, so we have one 8 kilowatt range. Okay, so 8 kilowatt, that's obviously above the 3.5. Our column B goes 3.5 kilowatts through 8 3/4, so anything less than that. So we're good here. We have one appliance. We go over to the column that matches it, and we have 80%. So we're going to get that 8,000, and we're going to get 80% of it, which for that, we just do times 0.8. And for that, we get 6,400 watts. Okay, so that's our answer, and our nameplate is what they tell us. So the nameplate said 8K or 8,000. But the demand is 6,400. So I'm going to transfer that right here. I'm just going to say 6,400 because next to it, volt amps. So our dryer is completely different. This is fun, right? You're having a good time? Okay. So for our dryer, our demand is always a flat 5,000. Okay? Our nameplate is what they give us. So what they gave us was 4.5 kilowatts. So thousand, 4.5 thousand watts for a dryer. Okay? And now you simply look at both of them and say, which one's bigger? Okay, 5,000K. So we're going to go 5K. So we're going to go 5K. Okay, I'm talking like you already understand all this stuff. So if I make a slip up here, there shouldn't be that big of a deal. Okay, and heat and AC are pretty straightforward. So for heat, we have 20 kilowatts. We just transfer it right there. That's all we do. AC, we have 40 amps at 240 volts. So I mean, you should probably already know this, but remember, to find wattage, we do volts times amps, or amps times volts. Either way works. So 240 times 40 is 9,600. But that's not your answer. Make sure to pay attention to the quantity. We have 2 AC units, each at 40 amps, 240 volt. So we simply are going to times that by 2, and we're going to get 19,200. Okay, now we simply look at both of these, and we say which one is larger of our heat and our AC. We have 20 kilowatts, 19.2 kilowatts. Okay, so it's 20 kilowatts. Okay, and next, we're just going to look for our largest motor, and we're going to times that by 0.25, or we're going to get 25% of that. And that's going to be our answer for this. Okay? So let's think, what here has a motor? What doesn't have a motor? Okay, you have a dishwasher. That might not have very much of a motor. You have a disposal. Okay, that's a definite motor. We could all think about that. We have a compactor that most likely, okay, is going to use a motor. And then we have our attic fan. So out of these 3, which is your highest, we got our compactor, which is 1 kilowatt or 1,000 watts. So we're just going to get our 1,000 watts. We're going to times it by our 0.25. So we're going to get 250 watts. And now we're going to get all of our totals which is our total demand lighting load right here. Our appliance load here. And then we actually need to, both of these are finalized. So our range and our dryer, we're going to add those together too, 100%. And then since we chose our bigger one here, we're going to only choose the 20 kilowatts, the bigger one that we chose. And then we're also going to add what we just did, our largest motor, 25% of that. Okay, let's add it all together and see what we get. You know, again, I'm just going to do it with you. Okay, so we got, well, actually, I pointed the wrong thing. You should have already known that, though. But our total demand lighting load, boom. Okay, so 4785 total demand load for lighting. It's what we're going to use. Okay. So now we're going to add our number after that 75% is taken off, remember? Okay. Or not taken off, but we're taking 75% of it. So do plus 5,772. Then we're going to do plus 6,400. Plus 5,000. We're going to do plus 20,000. It's good, you just type 20 and then 3 zeros. And then we have 250. For a total answer of 42,207 watts. Let's write that down. Ooh, that is actually great. I made a little bit of a mistake. I hope you caught it. I hope you were wondering what was going on. I didn't add this number. Something was a little off. Okay, so I'm going to add our 978. Don't forget about it. You just watched how I forgot about it. Okay, we're going to get our answer of 43,185 watts or volt amps. Let's write that down. And again, I really hope you know this by now. If you don't, you might want to do some more reviewing and on the job before you're here. So we have our final volt amps or watts. And since our house, you have your A and your B phase, that's all that you have in a residential home. So what we're going to do is divide it by 240 because you have 120 volts on each of those legs. So the max potential you're going to have in a single family dwelling is 240 volts. So let's do that. And the answer is going to give us our amps. So 43,185 divided by 240, we have 179.9375. Make sure you label each one so you don't get lost. We have our watts, we have our volts, we have our amps. Okay, now that we solved our amps for the entire house, now we can figure out that minimum overcurrent protection device for the dwelling, for the whole entire house. Okay. All right, you did it. This is our last table we got to look at. So we're at table 240.6a, which is on page 100 of the code book. And what we're going to do is we're going to get that answer, which was 179.94. Yeah, and we're going to look for that in this table. And if we don't find it, we're going to look for the next size up from that. 179, we got 175, and we got 200. So we're going to choose 200. 200 is the minimum size of our overcurrent protective device. So there we go. This unit is going to take a 200 amp main breaker known as your overcurrent protection device. So I don't know if I already mentioned this or not, but if I didn't, I will leave a link in the description that will have a document of this if someone asks for it. So just leave a comment saying, hey, I want this paper. I'll give it to you. Okay, so I also marked this with a large green tab. So then it's just quick and easy for me. Green, ground, you know? Okay. I'm going to talk about the stuff in the codebook in a second, but let's just figure out the neutral load real quick. Okay? So it's pretty easy. We got 100% of what we have here. So we just transfer it. 4,785. Here for neutral, it says only 120 volt loads 3 or less use 100%. Okay? So this says same. Oops. This says same. So we're going to get the same thing over here. Our range and our dryer do say 70%. So we're just going to take those numbers, multiply them by 70. So we got 6,400 times 0.7. We got 480. I want my handwriting to be readable. Okay, then we have 5,000. And we have 3,500. Okay. And then when we go down to where it said our largest motor and we took the 25%, we just take 100% of that. And now we're going to add those numbers together. So we got 4,785, 5,772, 4,480, 3,500, and 250. So we have 18,787 volt amps. So we just quickly solved our neutral load. Okay, so now let's go into the code book a little bit. Let's kind of talk about why we're doing some of these things. Start from the very beginning. We're going to go to that why subtract 3,000. So we're going to go to table 220.42. So here are your demand factors. Demand factor is simply saying you're taking a percent off. And oh gosh, I always like to highlight my demand factors blue. I almost missed that. Okay, so it tells us the type of occupancy, portion of lighting load to which depends, which demand factor applies in volt amps. And then here's our actual demand factor or a percent off. So we're looking at dwelling units. So we started off saying, and dwelling units, you go first 3,000 volt amps are at 100%. Then from 3,001 to 120,000, you have 35%. So that's why we took off the first 3,000, took it away, we held on to it. Then we took the remainder, which the remainder is 301,002. It normally never goes to 120,000. And if it does, there's a rule for that. But we're going to start with this. We're going to have, it's under 120,000, so it fits in this category of 35%. So we took our remainder after taking away that 3,000. And we times that by 0.35. And then we get that answer. And since our first 3,000 is at 100%, that's why we simply take our 3,000 and we add it back at 100%. It's just a simple way of solving for this, okay? So it just helps you solve it quickly. By the way, we are on page 76 of the codebook. And if we just flip it on the next page, 77, we're here. And now we can look at two things. First, we can look at small appliance branch circuit load. This literally says, in each dwelling, the load shall be calculated at 1,500 volt amperes for each 2-wire small appliance branch circuit. So, in a single family dwelling, you're just gonna have 2-wire. So you just know that. It's not you only have 2 wires in there, it's the wire that's feeding it is a 2-wire type of wire. So it's a hot and a neutral. It's 120 volts, so it's hot and neutral. Then we go to that laundry circuit load. A load of not less than 1,500 volt amperes shall be included for each 2-wire laundry branch circuit. So that's why here we did the 1500 and we did the 1500. And we took 2 small appliance branch circuits because in a house you have at least 2 small appliance branch circuits always, minimum. Now we can look at our appliances and how we had that 75% demand factor. Well, right here it says appliance load in dwelling units. It shall be permissible to apply a demand factor of 75% to the nameplate rating load of 4 or more appliances. And then here you have some gray section. So if you have a gray section or you have like a delta symbol, this means this is the new code of 2020. Before this wasn't even in here. So I'm really glad they actually included this, because without this, it was just kind of like, you kind of just had to memorize this. So if it's rated at 1/4 horsepower or greater, so anything under, in other words, anything under 1/4 horsepower or anything under 500 watts shall not be applied to the 75% demand factor. Okay? And then it also says this demand factor shall not apply to household electric cooking equipment that is fastened in place. So that's why we didn't do that. Our clothes dryers, our space heating equipment, and our AC equipment. Let's talk about space heating. What is a space heater? A space heater is any heater that heats a space. Literally. So then we have our non-coincident loads. I'm getting freaking tired. Sorry. Where it is unlikely that 2 or more non-coincident loads will be in use simultaneously, it shall be permitted to use only the largest load. So that's exactly why we did heating/cooling. These are considered non-coincidental loads because you're probably not going to be running your air conditioning and your heater at the same time, although rich people sometimes do. So we're going to just take one of those. Okay? Next, I want to show you how good these tabs work while going to our full load current table for single phase AC. Okay, and okay, I was at the wrong table. See, I told you I'm getting tired. We're going to go to table, I did show you the tabs though, 250.55. Okay, we're going to talk about this a little more. Just wrap your head around it. So we already talked about column A, column B. So what happens if you have column C? Column C is if you have not over 12 kilowatts. So anything that's over 8 3/4 rating, kilowatt rating, to 12,000. So 8 3/4 to 12,000, and nothing over 12,000. You're going to use this column. And in these columns, I highlighted demand factor, then I highlighted these columns, so it's yellow, so these are demand factors. I highlighted this orange, and I highlighted kilowatts orange, because these are just kilowatts, okay? So let's say they said, okay, we have a unit, it's 12 kilowatts, and we have 3 of them. You're going to go to number of appliances, 3. You're going to go over, you're going to see 14 kilowatts. So if you have 3 appliances at 12 kilowatts, you're actually going to math all those out at 14 kilowatts. That's your answer. Here's a kind of cool bonus at the end of the video. Okay, so we have our overcurrent protection device, our main breaker. So now what size wire can we bring from that breaker? Just 200 amps, right? No. We got to rate it at a continuous load. So we got to do 25% over. So we go 200 amps times our whole number plus the 25%. So it's 200 times 1.25. So we got 250. So now that we have 250 amps for our wire, what size can we put on 250 amps? Okay, and for that, we go to table 310.16, ampacity. We look for that 250. 255 right there. We're going to need 250 kc mil. Remember, anything over 100 amps is here. Anything under 100 amps is here. So we're over 100, 250 kc mil. Okay, and if you're thinking, oh, 250 amps, 250 kc, don't even think that, because that will not work for anything else. I've never actually seen that work like that before. That's really cool. So there we go. We did load calc. We got our overcurrent protection device is what they asked for. We also solved for our neutral, and we found our wire size that we can put into that overcurrent protection device. You have any questions, please leave them in the comment below. I would love to answer them. Like I said, if one person asks for that worksheet that I was using to work on this, I will be happy to leave it in the description. Good day to you, and good luck.